Okay, so once again, this is Sudh Pandey, and you are floating in physics along with me. So, as you know, we are going through a topic. That topic is a part of the chapter. The chapter name is Mechanical Properties of the Materials, and in that chapter we have finalized our first topic, and that is the elasticity. And now we have come to the next topic, and the next topic is surface tension. In the previous lecture I have explained what is surface tension and what is the reason behind the appearance of this surface tension, which we can found on the surface of any liquid. So this is a unique property which is we can say that just similar to elasticity as in case of solids. So I have told you that how there are certain forces in different type of molecules. Means one molecule which is inside, or we can say in the deeper of the liquid, and the other molecule which is on the surface of the molecule, and both molecules feels different types of forces. The molecule which is we can say that is in deep inside the container, that feels the forces by the neighboring molecules in equal amount, and that's why we can say that the molecule which is inside feels symmetric forces. But the molecule which is on the surface of the fluid, occupied by the certain region filled by the molecules which are of air, and some of space is filled by the molecules of the liquid itself. So, if we talk about the molecule of the surface, then the force will be asymmetrical in the nature. So, these things I have explained to you in the previous lecture. And this is the major cause for the appearance, for the development, for the existence of the surface tension. Now, in this lecture, we will see some more interesting things, examples, and there are so many things we can simply say which we have to go through. So, let's get started. As you know, the fact that a liquid surface has the property of surface tension can be demonstrated by a number of simple experiments. Means you can say that we have came to know that there is a property, a special type of property on the surface of the liquid, the property named as surface tension. Now how we can believe, how we can say that is this property in real. So for that we have some experiments here. Let us look them. So this is your first demonstration. Demonstration means an activity you can perform also at your home. Okay. So the first demonstration is there, and in this demonstration it is clear written that we take a ring, and the ring that is made of wire. Means wire, maybe it is of copper, maybe it is of any metal. Okay. So and now we have to dip it in a soap solution. Now the question is this, that why we use the soap solution. We can take a simple water, because simple water is also fluid, and it also has surface tension. That's why a mosquito can resides on the surface of the water. Clear? So if there is a no property of surface tension, then how the mosquito can reside or can stay on the surface of water? So why we can't take the water here in place of soap solution? So we take soap solution. The reason is that soap solution has itself a unique property. And what is that property? It has dual layer, we can say. So dual layer means if we compare the soap solution with a normal liquid or normal water, then if water have surface area A, then the soap solution has surface area 2A. And if we draw a length for calculating the surface tension L on the water surface, then in this case we have 2L. So in practical we can easily identify the surface tension in soap solution with compared to the liquid, or we can say pure water. I hope that now you clear that why we are using the soap solution for the demonstration of surface tension. Okay, now what we have to do, we have when the ring is taken out, a soap film bounded by the ring is formed. So it is obvious that when you dip that ring inside the soap solution and very smoothly, very gently, when you take it out, then you will see a very thin film over there. Film means a layer. So a layer which occupied the entire circumference of the ring. Clear? So now what? Now take a loop of thread. You have a thread, a very means we can say that a thread which has less weight. So very light thread you are going to use here, and when we take a loop, then wet it and place it gently on the soap film. So firstly, what we have to do, we have to wet it, and then we put that thread on the liquid film, or we can say that the soap film. So you can imagine that this is the study of only the layer. So and layer is made of liquid, not any solid material. So you can put anything like this way, or you can drop anything. But it is a liquid film, so it is very sensitive. So we have to handle the scene very carefully, very gently, very smoothly. Now we gently place that thread on the film. So is it clear? Okay, now what? The loop stays on the film in an irregular fashion as it is placed. So you can see in this figure, you can see that this is your the thread loop what you have placed, because you cannot give the thread to a unique shape by yourself. You can only simply wet it and just place that thread on the liquid film very gently. Now what? Because the shape of the thread what you have put on that film is irregular. Irregular means not a definite shape. It will not will be in the shape of circle, it will not in the shape of triangle, it will not in the shape of the square or whatever. So that shape is called irregular shape. And then the miracle starts. Now if prick a hole in the film inside the loop. So when you prick a hole on the loop, and if we can say the inside the loop with a needle, means as we have a balloon filled with the air, and just take a needle and prick that, then what will be burst. Okay, so that scene will be created here, but there will be no pop-up sound. Okay, so we can say simply that as we prick a hole in that film, in that liquid film, the process is very gentle, clear. You cannot take just take any needle and just put like this way. So that will be very smoothly, very gently. You have to make a hole in the or we can say inside the loop. And loop, what type of loop? Loop made of the thread. Then you can easily see, what we can see, that the thread is radially pulled by the film surface outside and it takes a circular shape. So in this diagram you can see that now the irregular shape of the thread is completely becomes a circular as the shape of the ring. So this demonstrates that some stretching force appears, means the surface tries to stretch itself. This is the basic concept of the surface tension. This is happened due to surface tension. So I hope that now it is clear that there is a certain property and we named that property surface tension. You can visualize this property by yourself by demonstrating this experiment at your home. Okay, now what? Now we can simply took to the next experiment, or we can say the next demonstration in front of you. In this demonstration, what we are going to do, just take a U-shaped frame. Take a U-shaped frame of wire on which a light wire can slide. So you can see that this is a frame here, this one is your frame and this one is your sliding wire. So sliding wire can slide on the frame. So I hope that this is now clear. Okay, now what? Now dip the frame in a soap solution. Again soap solution we are using here, and take it out. Means we can simply say that we have taken a container filled with soap solution and the film is dipped in it like this way. This is your soap solution, we assumed that. So as you see, you can see here that the frame, whatever frame we have created here, that U-shaped or rectangular shaped or whatever you can easily handle, you can. So that frame is now dipped inside the soap solution and gently pushed out. Because if there is any trembling, when any shivering in your hands, then this demonstration will be not going through properly. So we have to very take care of the sensitivity of the demonstration. This is very sensitive experiment, so take care of it. Now we have to what? We have to pull it back. Now what? A soap film is formed between the frame and the sliding wire. Means when we see finally after taking it out, we find that we have a thin film and film made of soap. Like this way we can say, and if this is your frame and this is your sliding wire over it, then you can see a film, very light film, very thin film, like this way. Clear? This is very interesting. You can see by yourself. Okay, this is like this way. You can see very light film, very thin film over there. So this is like a transparent window. As you can see that in your window there is a glass fixed on it. In the same scene, in place of glass, a soap film will be there in that frame. Okay, so now what? Now we have to place the frame in horizontal position, and the friction is negligible. As we assumed here, the sliding wire quickly slides towards the closing arm of the frame. So as we place the frame horizontally, then we see that in a moment the sliding wire starts to slide towards the closing end like this way. So it will start from this direction, or we can say towards the closing end. Okay, this shows that the sew film in contact with the wire pulls it parallel to the surface. It is obvious that your wire is sliding, which is the direction parallel to the surface, and if the frame kept in vertical position with the sliding wire, at the lower position one can hang some weight from it to keep it in equilibrium. So now what we are going to do now, in this statement it is clear written that now if we put, because we have seen here that if the frame is in horizontal direction, means as you see that this is your frame, this is your sliding wire, this is horizontal position, then the wire starts slide toward the closing end. It means it slides parallel to the surface. Okay, so what will happen if we put that frame in vertical direction, means like this way. We have put the frame like this way, as you can see in this diagram also, and this is your sliding wire. Now as you know that the sliding wire tries to move upward towards the closing end of the frame, and if we want to maintain the position of the wire or sliding wire, then what we have to do, we have to gently place some weight over it so that it cannot pulled by the surface of the fluid, and it will remain in its stationary position. So whatever amount of force we can say applied by the surface due to the surface tension, that must be balanced by the weight what we hang over the sliding wire. And if these two forces are balanced or equal, then this is the condition of equilibrium. Okay, now the force due to surface tension by the surface in contact with the sliding wire balances the weight. So this is basic, you can say that we can simply say that surface has some force, some tension over it, and the surface tension is basically exist only on the surface of any fluid. So these two experiments, these two demonstrations are very unique for the demonstration of the surface tension. Now there are several examples you can take here, that we have a example of paintbrush, we have the example of residing of the mosquitoes, we have the example of when we throw some kerosene oil on the water, then it will float on the surface. So there are different examples, different daily life experiments, daily life activities which demonstrate the surface tension, but as we don't know the term surface tension, that's why we ignore that phenomena and simply see that mosquito is residing only on the surface. But why it is residing, we don't know. We simply gently dip our paintbrush inside the water and pull it back, but we don't pay attention what is the pattern of the brush. So these are the daily life examples, you can simply say, which demonstrate clearly about the surface tension, that the surface of any fluid has some specific property. So I hope and I believe that this topic is now clear to all of you, that how we can demonstrate the surface tension in our home, in our lab also. Okay. Now, finally, we have, or we can say, we can not have, we can conclude that due to surface tension, the surface of any fluid has a tendency to decrease the surface area, because when we have placed the thread, then thread occupies the shape of the ring, because the surface just start to shrinking or decreasing. It means whenever there is any opportunity to the liquid surface to shrink it, then it tries to decrease the surface area. Okay, so here is written that the property of surface tension may also be described in terms of the tendency of a liquid to decrease its surface area. What does it mean? It means simply we can say that in the previous lecture, or the lecture before this heading, we have a formula, and the formula demonstrates that the surface tension is the force per unit length. It means surface tension explains the force experienced by the imaginary line drawn over the surface. But here I want to explain that the surface tension not only explains about the force, but it also explains a tendency of decreasing the surface area, as I have demonstrated you that when we place the thread, then it tries to shrink. It means in case of surface tension, there are two rules. One is of force, and one is of decreasing in surface area. So surface tension, we have to study about the surface tension in two prospects. One is your force and other is your area, or we can surface area of the surface. Okay, so it is written here that because of the existence of forces across any line in the surface tends to shrink whenever it gets a chance to do so. So these statements I have already discussed with you. So there are numerous examples which illustrates that the surface of a liquid tries to take its minimum area. When a painting brush is inside a liquid, the bristles of the brush wave freely. When the brush is taken out in the liquid, surfaces are formed between the bristles. To minimize the area of these surfaces, they stick together. So these are the examples which tells about that surface area has surely a tendency, so that it whenever there is a chance, then it tries to shrink itself or tries to decrease the surface area. So this is the tendency of the, you can simply say that this is the tendency of the surface tension. Okay, now a small drop of liquid takes nearly a spherical shape. This is also the example of surface tension, or we can say the tendency of decreasing the surface area. Okay, this is because for a given volume, the sphere assumes the smallest surface area. So if we take different types of designs, like triangle, like circle, like cone, we can say in 3D. So the minimum area can be taken as a sphere. That's why a liquid drop or whatever drop, raindrop we can say, occupies a spherical shape by due to the existence of surface tension. Okay, raindrop is not like a cylinder. This is not the shape of the raindrop, but the drop is like this way, like spherical. So it is also because it tries to decrease its surface area, and the decreasing surface area in 3D, that is assumed to be a sphere. So it suddenly takes a shape of the sphere, not as a cylinder, not as a cone. Okay, so this is all about today's lecture, and we can simply say that if we from the first lecture to up to this lecture, we can finally conclude that the surface tension basically, or we can say surface tension can basically give the two things. One, that how much force is felt by the liquid surface, and other one is that due to the change in the area, because area is decreasing in case of surface tension, or we can say that the layer of the liquid tries to decrease its surface area, so we can simply say that there is a force and there is a displacement, so there must be some force, or we can say that some type of work done, and if there is a work done, then there must be some energy, or we can surface energy. So finally we have a result that if we know about the surface tension, then we either can go towards the force, or we can go towards the surface energy. So surface energy is basically we can use when we are study about the tendency to decrease the surface area, and when there is no chance of the surface to decrease its area, then only simply we have to go through the force experienced by the layer. So finally we can again conclude that we have two scenes created here. In first scene, the liquid layer is in stable situation, we can assume little bit. Okay, and in the second situation, the liquid layer is in motion, that's why it is decreasing surface area. So when we assume the surface at rest, then if we go through the force, and when we say that the surface is in motion, then we go through the surface energy, because some work is done by the liquid surface in that case. Okay, so I hope and I believe that this thing is now clear in your mind, like a clear film. Okay, so we will continue your lecture in the next class. Thanks for listening me, thanks for watching me. Okay, thank you very much.